Let me check the schedule a little bit. Okay, looks like okay. I'll think about the fact that maybe we will be doing like an online lab, not lab. I mean the quiz session, so that all of you would be fine with your own schedule. Okay, so this final lecture, not final yet. I mean we have another two, but this is like before Songkran festival that you would be able to relax and maybe anyway, so today we will go over what the technique that is called principal component analysis. But before we go to that topic, let us recap a little bit about what we have learned since last week. So what we've learned in last week was about the unsupervised learning. That was mainly like a learning category, or maybe like a types of learning that is basically about extracting the properties of the input features. So in this setting, there will be no target, which is opposed to the previous technique that we've learned before, that was supervised learning, that consists of the input feature and the target, right? So in this case, whatever techniques that we're gonna learn since last week, this week, and probably the next 2 weeks are going to be the techniques that are that have been developed for the unsupervised learning, where you will be extracting the signals or maybe the data properties, the input features properties, and in that setting you will not be able, or maybe you wouldn't have the access to the target of that input feature. So that's just like the setting. And okay, so as we mentioned before, if we are going to learn a model that captures signal structures or maybe the data structures without having the target, I mean, it's like the question is, what are we going to capture from these input features, right? What are the information that we could extract from this? In fact, any information that you will extract from the unsupervised learning technique are usually related to the following properties of the maybe the input feature. The first properties is like a feature properties. Such as orthogonality. Yeah. And maybe clustering is something along the line that, clustering that we've learned last week wasn't exactly about orthogonality, but about correlation of feature. Right. Actually, orthogonality and correlation are somewhat related. If the data or maybe the input features are orthogonal, they are uncorrelated. That is something. And another thing, let's say properties or maybe measurements that we normally use with this is the feature vector distance. So from last time, if you remember, we tried to maybe extract the cluster of your data samples using the distance of the input features that are closest to their neighbors or something like that. Or maybe you start off with having the centroid of the cluster, and then you try to find the cluster with the centroid that is closest to the data sample. So that is the kind of, like properties that you will be using when you're dealing with the unsupervised learning. So these are like the common things that people would do when they maybe when they are learning the model to extract some signal properties. In fact, there's another operation that we normally do with this unsupervised learning that is about the dimensionality reduction. So dimensionality reduction concept is something that is closely related to the orthogonality, but in fact it is about whether or not you can provide like a unique mapping from the original data to the reduced data dimension. For example, if you have xj being your training sample and you want to reduce the dimension, let's say you put it inside a black box. It could be like a neural network or maybe a machine learning. And then this black box return you like the set of output that is like a reduced feature dimension. Samples. Let's say if originally xj is in Rn, this set j may be in Rk, and k is much less than n. This is like dimensionality reduction because you pass your whatever input into some black box and you get like a reduced feature vector. But what is like the important feature that this black box need to have is the fact that once you reduce your feature, that feature should be meaningful. And to say that it's meaningful, that means that you are able to reconstruct it back to something that is close to your original feature. So usually people will say that the concept of dimensionality reduction is somewhat related to the ability to reconstruct it back. So dimensionality reduction and data reconstruction is like the default it's like a default operation that goes together. So you have reduction, and what you want to make sure is that whatever you reduce to, whatever your output compressed dimension was, it should still faithfully represent your original data. So that's why if you can reduce it, you should be able to reconstruct it back, right? And actually, as a byproduct of the data reconstruction from the reduced feature dimension sample is the interpolation, a bypass product. What is interpolation? Interpolation is very similar to reconstruction, except that there are some defects in your original input. And once you compress it into like a reduced feature sample, that reduced feature samples are able to capture the important information in your original data, even though it defects. And you can reconstruct like a signal xj hat here back, and xj hat here maybe happen to have the information filled out despite the fact that it came from something that is defect. So that is like what we call imputation, or maybe missing value interpolation. Actually, one of our example is going to be solving for missing value, and we will be using this concept to fill the missing information. So yes, maybe I'll show you. I'm not sure if I showed you yet, but it is like another example that people normally refer to is in painting application, that it is like this, like originally your original data maybe like a face of a guy that was missing, But once you are able to have like a projection matrix or maybe a neural network and the data at a compressed dimension that are uniquely represent the signal, you can use those reduced information to reconstruct that missing information back. Yep. That is like the concept. But that means we have to learn how to project, your data and faithfully represent it. And pretty much you can think of the neural network or whatever in the reduced dimension like a memory that you keep it when you do the training. And please don't forget the fact that whatever you're doing here, we still have the testing phase and the training phase. The training phase involved with how would you come up with this reduced dimension and what is this black box should be. So in your training stage, you train these two things. You try to train for the black box that's going to compress your data, and you try to train for the reduced feature dimension, or sometimes we call it latent feature. And usually like these two things will keep information about input. And because of that, when your input has some kind of missing value, these two components can help you reconstruct it back. So that's the concept of dimensionality reduction. But don't worry, we will not go very far from, like a normal metric vector projections. It's going to be something fairly simple today. Yep. Another application that is normally used in unsupervised learning technique is data association. So it's about the vector correlation. Let's say if you found that your data happen to be correlated to something like maybe you have let's say customers who are like watching movies, and you can somewhat using the correlation between customers or maybe the movies and genre to extract some particular ranking. So that's another application of unsupervised learning. Yeah. Okay, so just to keep in mind, the characteristic of unsupervised learning involve mainly two things. There's no ground truth, and also the measurements of these unsupervised learning, in terms of evaluation, is going to be quite subjective. Just like previously we have data association, ranking what people like. You have dimensionality reduction, which is about reducing dimension of the data, which is quite opposite to supervised learning, that you have like a target that defines what is the truth. You don't really care about the context. But in this case of unsupervised learning, you care about your context. You care about whether or not you're doing clustering. If you do clustering, that means whatever your target is going to be different from dimensionality reduction. Even though the underlying concept and techniques of data clustering, dimensionality reduction, and data association are all using the feature vector properties like the feature distance, the feature correlation, and the orthogonality. So usually they use these three properties of the feature, but it is like their products are different. One is about clustering, one is about finding, the correct projection, and another is about finding the correlation and ranking. So yes, you have to look at what you are doing. And according to that, you will set up some kind of evaluation rubrics to evaluate the performance. Okay. Sorry for taking too long for that slide. Anyway, next things we will go over. So what about principal component analysis? As I hinted before, the principal component analysis, or PCA, is going to be about dimensionality reduction. And yes, as we mentioned before, if we originally have an input feature, we reduce the dimension into some latent feature. Okay, let's call this one latent. which is like a reduced feature dimension vector. Okay, we have this dimensionality reduction. What we will also have is the reconstruction. That to ensure that whatever you have here as your latent feature will still faithfully represent your original data. Question is, why do we need to ensure this? Okay, let's just put it simple. If you have a picture of a person and you want to reduce that picture information, let's say if your original input feature has a dimension of 3 times height times width, 3 is RGB, right? And your latent feature may be in a size of 100, just 100. Thing is, you can do many things to have this reduced feature dimension vector. You can do many things. For example, you can sort for the maximum value of this X for 100 samples. And you say that that is the one that is containing, lower dimensional feature, so it should work. But the thing is, there's no guarantee that this 100 samples would be able to faithfully represent your entire image. So that's why there is another condition that, if you want this meaningful latent feature as your reduction, you should be able to ensure that you can reconstruct the signal back from your reduced latent feature. So that's like the main reason why we have to talk about reconstruction when we talk about dimensionality reduction. So it's like, even though your target may be just, reduce your feature dimension, but the bypass of this will be the reconstruction phase. That is like, you have to make sure that it's going to work as well. Okay. So, what is PCA? PCA is about the fact that it's actually a concept of finding the projection matrix phi here. And you can think of the fact that initially you may be having like input X here in Rn, and then you have this matrix phi. You can think of it as initially like a black box, but it could also be a projection matrix of size Rp times n. This means that if you multiply this with X, right? If you multiply like that, you will have a new vector set J that is of size Rp. And usually when we talk about PCA, P is much smaller than N. Or we would say that this is your latent. Okay, so that's your the setting for PCA. So why we need this setting? So as I mentioned before, yes, our concept is about reducing the feature dimension, but what is the reason that we want to do this? One of the reasons would be that we may be able to visualize our data in a much better way. For example, if you think about the input features that you used before, I think in your tree classification, if you remember, there was like a features about flowers, petal length, size, whatever. That data set, or maybe we can look at here. I think I provide the link for you as a PCA example. Yep. So this one will give you an example of the fact that, okay, if you have like these 1, 2, 3, 4 features, but you want to visualize, the feature clustering, or maybe whether or not what is like the most important feature among these 4, for all these data samples, you can actually use PCA to extract the principal component. And what does it mean by principal components? You can think of principal components like coordinates that will best represent your data, or it's like the coordinate for your latent feature. That is what PCA or principal components is. So yes, initially you may have these 4 features, but you can apply PCA to reduce from 4 features to just 2 components, from 4 to 2, like that. And once you have these 2-dimensional feature, you can visualize the distribution of your feature. And in this example, it's kind of look like this. And in here, they actually highlight the feature samples according to their classes. So now this is like, this 2-dimensional component PCA is like the visualization of that 4 features, and you can see how your samples are clustered. Red samples belong to one class, green samples belong to another, and the blue samples belong to another. And actually, if you're doing clustering, you can also apply clustering for classification. So definitely if you do clustering like, whatever we learned last time, k-mean clustering, for example, you probably end up with like 3 groups like this, and where you're going to have like the centroid of each cluster in the center. Yes. So yes, the concept of PCA and data clustering are somewhat related in this way. Like you have your PCA as the method to reduce your data dimension, or maybe for visualization, where you can see whether or not the cluster of your samples are making sense. Yes, so this is like the relationship between today's topic and the one previously. But anyway, you can follow this example for your coding if you want to apply PCA. Because I don't want to develop another code, but you can look at it. Yeah. Anyway, let us go back. Okay, that was like the application side, but today we will talk about the theoretical side of it. Okay, previously we've seen that we can actually reduce dimension of we can reduce the dimension of the input features of size 4 to just size 2 with principal component in 2D. So principal components, as I mentioned before, is like the coordinates. If you use 2-dimension principal components, that means you are creating like a 2-dimensional coordinates for your data. And these 2-dimensional coordinates should satisfy the following properties. First, it should provide you a unique mapping. Okay. Okay, let's talk about the fact that, if you have this xj as your data in 3 dimensions, you want to project it down to 2 dimensions. So that means you want to create a new coordinates in 2 dimensions for your data. So, like the projection towards the new coordination is like you have to multiply this xj vector with this phi matrix. And the one that convert from, project down information from 3 dimension to 2 dimension are these row vector of your phi matrix. Am I right? So you do the dot products, like phi 1, phi 1, phi 1, 1, phi 1, 2, phi 1, 3, dot products with xj1, xj2, xj3, you will have zj1. So that is like the value in one of your coordinates if you want to visualize your data in 2D. Meanwhile, another row of this phi matrix, phi 1, 2, 2, 1, phi 2, 2, and phi 2, 3, will be like another maybe projection for the second value in your coordinates. Or on the other words, it's like you have this three-dimensional data and you want to visualize it on 2D coordinates. So this planar will be your coordinates. Or in the other words, it's actually your phi matrix. And whatever projection that you get on your phi matrix here, this, if this is phi 1, if this is phi 2, then this is like your sat 2, this is like your sat 1, giving that your sat is like just like that. So as a visualization for you to know where things are. Is that okay? So you can say that once you made this projection, you can think of like, okay, this is the example in 3 dimension, but let me give you example of maybe 2 to 1 dimension. So you have like a point xy here, maybe x1, x2 is better. And you say that, okay, if you have 2-dimensional data, you can use 2 options for PCA. Either you have only 1 principal, or you have 2, because the maximum coordinate is like 2, because your original data is in 2 dimensions. So maybe let's just do just 1. So maybe if you come up with a phi matrix, like that project this data. So whatever you have here, that is your projection, this is going to be your sat. So it's like you're doing the products between x1, x2, and phi, which is like a row vector. In this case, it's going to be phi 1, phi 2. And once you do dot products, you're going to have sat 1 between 2 vector. So that is like the main concept of this principal component analysis. Or in the other words, this phi matrix is like, the projection matrix that gives you the new principal components or the new coordinates. And the value on your coordinate will be the z value. Once you do this projection, the important part is that you have to make sure that whatever you project here as sat could be recovered back to x. So that is like, if you have z and phi, you're solving for x, you're doing some kind of linear problem solving, right? It's like you have a matrix phi, x equal to z, and x is unknown, right? So if x is unknown, what you have to do? Right? So this is like solving a linear problem. Is it? Linear problem, like least squared. Let's just put it this way. And if you want to uniquely solve for x, you have to make sure that each of your equation here, like whatever z you have, you're able to map back to x. So that means that each of phi in each row, or maybe these 2 rows, need to be linearly independent. So that's your first property for your phi matrix. It has to be, the row vector of phi matrix has to be linearly independent to ensure the fact that you can recover back the x vector. But the thing is, checking for linear independency is possible, but it's not very easy. So people normally resort to another property that is called orthogonality. Usually, if you remember, if your row vectors are orthogonal, therefore they will also be linearly independent. So actually orthogonality, if I remember correctly, is like a stronger condition. But checking for orthogonality is simpler. So that's why we normally do it this way. So the first properties that your PCA has to have is the unique mapping. Okay, and this unique mapping can be checked using orthogonality of the row vector in your projection matrix. So that's your first property. Your second property is what is called the energy conservation. So what energy conservation means is that, okay, let's say if you have your X data here and you want to make sure that whatever data that you reduce to this are consistent, another way to check that is to ensure that the energy of your data before and after are about the same level. So on the other word, that means xj1 square plus xj2 square plus xj3 square is equal to zj1 square plus zj2 square. They should be about the same. So that means that's the meaning of the energy conservation, which is this one. Or as I mentioned here, but usually they are approximately, not exactly the same, but approximate. So that means if you want to make sure the projection matrix is working, right? Like working in terms of making this data reduction and be able to guarantee for reconstruction, then you have to set up the optimization problem that ensure these two properties, the unique mapping and energy conservation, which shall be constructed as follow. Shall we go? Shall we go? Okay, so here is how we formulate. Sorry, I just give the lecture in the morning. So it's kind of like that. Anyway, so this is your setup. You can solve for your first row and second row. Well, in this case, let us look at the original problem. Actually, the first row and second row of your phi matrix are going to be solved independently. So let's say if you reduce your data from 3 to 2, you have like 2 optimization problems. If you have n input features and you want to have like, many axes of these principal components, then that means you have that many optimization problems. But please don't worry, we will give you like an alternative view which reduce this problem into just one optimization problem. But let us look at each of them first. Okay, so firstly we say if we want to have the first principal component is like your first coordinates. The thing about your first coordinates is that, well, you just solve for this one row of your phi matrix. But if you want to also solve for your second row, you have to ensure that your second row is going to be orthogonal to your first row. So that becomes like the additional constraint. So if you compare between the first and the second principal component, your first will only have this like orthogonality as in correlation of its own signal equal to 1. But if you want to solve for the second principal component, you would then have this orthogonality between phi 1 and phi 2. I mean, the row 1 and row 2. But if you have 3 components, then that means your third principal component will also have to do the argmax on something which we haven't yet talked about, but subject to first phi, maybe I'll just shorten it as phi 3 transpose phi 3 equal to 1, and phi 3 transpose phi 1 equal to 0, phi 3 transpose phi 2 equal to 0. That is to ensure that, it's going to be orthogonal, and, highly correlated to itself for orthogonality. Okay, so that is like a side note. Okay, let us now look at the objective function of each of these optimization problem. So if you look at them, actually what this main objective function is doing is about, they want to ensure, okay, the orthogonality already ensure the unique map. So what is left is to ensure the energy conservation, and that is ensured by using the objective function. So each of these objective functions are actually ensuring the fact that, you want whatever is that here to have the highest energy possible from your data projection from X here, so that, satisfy the rules. And if you have 3 optimization problem, that means you are maximizing set J1 in here, set J2 in here, and if you have set J3, you can do it here as well, right? And the thing is, because all of these components that we are talking about is like the set here is not explicitly represent your phi matrix. What you really want to solve for is actually your phi matrix, and set will be the bypass product because it's like the projection result from X and from X and phi. So that means you have to decompose your set into phi times X here. Therefore, if you solve for each optimization problem, you're gonna have, your phi vector 1, your phi vector X, your phi vector 2, your phi 3, like that, right? And another thing to notice about is that, notice that when we do the summation over J, where J denotes the index of the samples in your training, or maybe your data samples, not about your feature dimension. So that means you are ensuring this energy maximization or energy conservation for all the samples that you have in your training data. Meanwhile, when you look at the constraint only limit on, provide the restriction on the feature dimension. And please don't forget the P is like the reduced feature dimension. Yeah. All right, that's like the original setting of the problem. Okay. Then I think the next question will be, so how are these related to the connection of eigenvalue and eigenvector? I believe that if you remember when we talk about orthogonality and all that, you probably remember that, one of the special types of matrix is that they are containing the rows or the columns that are orthogonal. And actually the eigenmatrix could be one of those. If you remember, not every eigenvectors of a matrix are orthogonal. But if you have the symmetric matrix, then very likely you're going to have the orthogonal vector. Do you remember that one? Kind of. Yep. Okay. All right, but before we go over that, let's look at, what is the relationship between the PCA problem and the eigenvalue and eigenvector. Actually, spoiler alert, that phi matrix is going to be the matrix of your eigenvector if it's actually the solution to this PCA problem. Okay, so let us look how they are related. So first of all, let us go back to our original setting where we have, your phi matrix to be the matrix that you project your original data. And here, I just try to decompose them into a way that I can explicitly represent the row vector of your phi matrix. And in here, we will only focus on the first principal component first. So, okay, this is the one that we are looking at, right? So in order to, reshape from this term into this vector matrix projection, we actually make a little tweak. That is, we concatenate our training data samples together, where if you remember, this one is like xj, this is just one sample. But to extend from xj to maybe x matrix, we actually concatenate the data along the column direction. And that will be our x transpose. And this x transpose times x here will be equivalent to doing this dot products multiplication and sum square. The reason that I can write it this way is because the dot products between phi row vector here and xj here, please don't forget that this is already a row vector. We don't need to do the transpose. If you do the dot products between the two, it becomes like a scalar value. So whatever you're doing here is like you are extending the sum square of the scalar value. Therefore, if you write it this way, you still end up with the scalar value. To keep in mind. That's kind of the reason why we can extend it this way. Right. And our constraint remain the same. That is the dot products between that particular row vector is going to be 1 for orthogonality. So let us simplify the look of this optimization problem a little bit by assigning v vector as a vector of this phi 1, just like that. So actually we are solving this optimization problem. And if we remember, we are solving like the maximization problem subject to something. The easiest way to solve this is to use Lagrangian, right? So that we don't need to iterate over all the constraints, right? And actually, if we solve this with Lagrangian, we will find that the solution to this problem for V is actually V has to be the eigenvector. And if this is like your first principal component, it will be the eigenvector with the highest eigenvalue. So that's the important point. But we will look at how this becomes that solution. Okay, so as I mentioned before, we start off with having this optimization problem. Then we recast this as the Lagrangian. If you remember last time that we learned support vector machine, we also have the Lagrangian. But that time we compute the argmax of infimum, but this time it will be supremum because we are solving the argmax problem. After that, we will negate this with the Lagrangian multiplied with the constraint, right? And then to compute the supremum, we have to find V that enable the supremum of this term. And we can do that by finding the stationary point. That is the point that causes the gradient of this objective function to be equal to 0. So we will take the gradient with respect to V vector. That means this vector will be gone, that vector will be gone. So we end up with alpha times V here, and for the terms before, that's going to be x transpose x times V equal to 0. So you have x transpose x times V equal to alpha transpose V here. And actually, this is the definition. If you look at the definition of the eigenvector and eigenvalue, you remember that, well, actually, the definition of eigenvector and eigenvalue are any pair of scalar value and a vector that enable the equality between A times lambda I, maybe let's say S here equal to 0. If this is eigenvector, if this is eigenvalue, it will be equal to A, right? For any matrix, you can always decompose this. Okay. So it's like your solution is actually to be something that satisfies this condition, but it happened that whatever pair of alpha and V here that satisfy this condition are eigenvalue and eigenvector. Okay, another thing that you have to notice about is that whatever eigenvalue and eigenvector that we are trying to extract here are going to be the eigenvalue and vector corresponding to the matrix X transpose X. And in fact, X transpose X will result in some symmetric matrix. And if you remember, once we extract the eigenvalue and vector of a symmetric matrix, that eigenvector will be orthogonal. That means any set of the eigenvectors that correspond to, any eigenvectors in the set of the eigenvectors of this symmetric matrix, they will orthogonal to one another, right? If you remember that properties, okay. Yeah. So that is the relationship. And if it was like the vector that, maximize this energy, or maybe this value, which is, you can imagine in that it's actually sat transpose sat. That means it has to be the one that gives you the highest projection, and that highest projection value will be the eigenvalue. So that means that this will be the largest eigenvalue for your first component. Or you can think of the fact that if you want to, project this matrix, find the best principal component to maybe some 2D points. If it was really the first component, that means it has to be a vector that pretty much mostly align with your data point. So it shouldn't just look like that. It should be somewhere that look like, a vector that goes through most of it. So that will be your first principal components. And kind of like it's the reason why it normally be the eigenvector with the largest eigenvalue, because it's the most important coordinates that can capture most of the value. Okay, so in these slides, I just emphasize everything again, that yes, because we want to make sure that the V vector will give the highest energy, then that means that it has to be the eigenvector with the largest eigenvalue. But the thing is, okay, this is something like a side note. If we have like a two-dimensional data like this, let's say if we have the first component, that should be the first axis, or maybe the first coordinate that goes through most of the point. Just like that. Your first PCA should look like that. But the thing is, what about your second? Your second will have to be orthogonal to your first. So usually the second one will be something like this. But your second one will be the one that captures much lesser information compared to your first one. Because if you think about the projection on these coordinates, there will be a lot of overlapping, like this dot and that dot is very close to one another. Meanwhile, if you think about, your first component that is on this direction, it's actually well spreading in terms of the data projection. That's kind of the reason why it captures most information, but your second component will usually capture the least information because it's the opposite of one another. Shall we move on? Okay. All right. In this example, I'll provide a little recap about how to do the eigenvalue, eigenvector decomposition. Do you want to go over a little? A little. Okay. Let's say if we have an A matrix that is symmetric matrix, we can use the following properties to find eigenvalue, and you can use another, another linear relationship to find the eigenvector once you have the eigenvalue, right? So if it's just 2 by 2, I believe it's not difficult. That is, you find a det, you just construct it up, and you have this det, and if you, I'm not sure, but in my country, people would normally do something like, if we multiply down, we multiply it up. Multiply down is like lambda plus 5 times lambda minus 4, and multiply up is like negative of negative 14. Yeah. And then we add them together, it's going to be lambda plus 5 times lambda minus 6 plus 14 equal to 0. จ้าแก้ได้แล้วใช่ไหม
แก้ได้แล้วครับแต่ว่าปัญหาคือลำชิมวิวไม่พอครับ
อ๋อโอเคจ้ะsomething like this, right? 14, sorry. Yes. And then once you do already reduction, you will end up with this equation. And then you can solve for lambda. So you have lambda equal to 2 and lambda equal to minus 3. So you will use your first lambda to find your first eigenvector. And then you use your second lambda to find your second eigenvector. Okay, so for your first lambda, you just plug it in and solve this linear equation to get V vector. All right, you can do some technique called reduced echelon. I think the hardest thing about this is this step. I normally get confused in this step, but don't worry. Every person has different problem with this. But anyway, and for the second eigenvalue, you also do the same things. You solve for V, and you get this second eigenvector. Notice that these two eigenvectors are not orthogonal because your A matrix are not symmetric. So this is like an example. But if you want to, look at the background information, you can use this link. I actually added here because for me, this is something I learned a long time ago. Okay, can't really open it up. You can try to, okay, I'll just show you what the site look like. It's actually look like this. It's like it provides you the information of what the eigenvector are, what the eigenvalue are, and then you go over what is the theory behind them, what's the properties, what can you check about them, or the example in 3 by 3. Yep. Okay, go back. Anyway, for me, this is just recap for the class in the morning that generally eigenvectors of any matrix is not orthogonal. But for the matrix that is symmetric, it's orthogonal. Just to recap, because a lot of people would get confused from this step onward. Anyway, let's take like a 5 minutes break. We will look at the alternative view and go through an example, maybe like a use case of this PCA.